Welcome to lecture 37 on essentials of topology. In this lecture 2, we will continue the study of the concept of connectedness. Specifically, we will see the union of two connected sets or an arbitrary family of connected sets. We will study the connectedness of continuous image of a connected topological space. Further, we will continue and we will study the product of connected topological spaces. Begin with the concept of union of connected subsets of a topological space. Let us see an example. If we are having a set X consisting of elements A, B and C, and the topology tau on X is discrete topology. So we are taking this topology as discrete topology. Now let us take two subsets of this X, and these are the singleton sets. Why not let us take A or A1 as the singleton set A and A2 as a singleton set B. Note that singleton sets are always connected in each and every topological space. Therefore, A1 and A2 both are connected subsets. But if we are taking their union, that is A1 union A2, this is a set consisting of A and B. In discrete topology, this is disconnected. From this example, it is clear that union of two connected subsets may not be connected. So, question is, can we put some restriction or we can put some conditions so that union of connected sets can be connected? Answer is yes, and that is given in the form of this theorem. This theorem states that if we are having a topological space X tau, and let us take a collection of connected subsets of X such that the condition which we are putting here, that is intersection of EI, I belongs to I is non-empty, then union of EI, that is union of connected sets, is connected. In order to prove this result, let us take this union of EI, I belongs to I, as a set E, and let us assume that this set is disconnected. So just we are assuming it, and we will show some contradiction. If this set is disconnected, what will happen? We can find out two subsets A and B of E such that these subsets A and B are non-empty. A and B are open subsets of E, that is open with respect to relative topology. They are disjoint and their union is E. Now if we are taking any element X in this intersection, because this intersection is non-empty, so it is clear that X belongs to EI, and if X is an element of EI, so X belongs to this E, which is equal to A union B. But A and B are disjoint, so it is clear that either X belongs to A or X belongs to B. Note that X cannot be element of both A as well as B. Now, as E is equal to union of EI, I belongs to I, and every EI is a subset of this E. As this E has a partition, therefore, what we can conclude? We can conclude that EI is a subset of A or EI is a subset of B, and this is for all I in I. Now, if we are taking x in A, then we can conclude that this EI is always contained in A for all I belongs to I. And it follows from the fact that if we are taking this is the set E and its partition A B. Now if we are taking X in A, note that X is member of intersection of EI, I belongs to I, as EI is either in A or EI is in B. Note that X belongs to A. Therefore, it forces that every EI will come inside A. And if every AI is a subset of A, what we can conclude that this union of EI, I belongs to I, is also a subset of A, or this E is a subset of A. But what we have seen, we have taken a separation of E in terms of A as well as B, where B is non-empty. So it contradicts that this pair AB is a separation of E. Similarly, if we are considering the second case, that is X is an element of B, what we can conclude that every EI is subset of B for all I in I, and this when we are taking if X belongs to B with the same justification as if this is E and if this is the separation A and B, let us take an element X here, and as X is member of their intersection, so if the EI will lie inside B, and if it is so, we can conclude that this union, this is also a subset of B, and it contradicts the fact that this pair is a separation of E. Hence, in any case, if we are assuming that this E is disconnected, we are getting a contradiction. Therefore, this union EI, I belongs to I, is connected. Moving ahead, herein we will discuss the connectedness of continuous image of a connected topological space. This theorem states that if f is a function from a topological space x tau to this space y tau dash, and that is continuous to as well as the topological space x tau is connected, then fx is a connected subset of y. Again, we will prove by contradiction. Let if possible, let fx be disconnected, then there exist again two subsets A and B of this f of x such that A and B are non-empty. A and B are open subsets or open in fx. They are disjoint, and fx is nothing but union of A as well as B. As this function f is continuous, what we can say that as A and B are open in fx, it says that this f inverse A and f inverse B are tau open. Also, if A and B are disjoint, from here we can conclude that f inverse A intersection f inverse B is an empty set, that is they are disjoint. And finally, this x it can be expressed as inverse image of A union B under F, that is X is equal to F inverse A union F inverse B. Also, A and B are non-empty. It means that inverse image of A under F is non-empty and inverse image of B under F is also non-empty. From here, what we can conclude? We can conclude that this pair F inverse A, F inverse B, this is a separation of this topological space X tau. It means that this X tau is disconnected, which is a contradiction. And therefore, Fx is a connected subset of Y. Moving ahead, the above theorem can also be written as continuous image of a connected topological space is connected in case if we are taking f of x is equal to y, meaning to say that this f is a surjective function. Then what we can say that if f is a continuous surjective function from a topological space x tau to y tau dash, where this x tau is connected, and this function we have already assumed that this is continuous plus surjective, then we can say that this y tau dash is also connected. So using it, we can conclude that connectedness is a topological property. That is, if we are taking a homeomorphism from a topological space x tau to y tau dash, this is a homeomorphism, and we are taking this space as a connected topological space, and from the previous result this is clear that this is also connected. Using the above concept, we can justify that the quotient space of a connected topological space is connected. Justification is simple because we are familiar with the concept of a quotient map Q. Let us take this map is from a topological space x tau to a topological space A tau q, where this tau q is quotient topology on A. We have already seen that this q is a continuous and surjective function. Also, if we are taking this space as a connected topological space, let us assume it, then from the previous conclusion we can deduce that this is also connected. That's the proof of this statement. Moving ahead, let us discuss the connectedness of product space. Begin with two topological spaces x1 tau 1 and x2 tau 2, which are connected. What we can show that the product space, that is x1 cross x2 along with the product topology, is connected. In order to prove this theorem, let us begin with a simple notion. If we are taking an element x2 in x2 and we want to see that what this set is, that is x1 cross x2, note that this is a subset of x1 cross x2. Note that we can put a relative topology on this set, and that will be with respect to the product topology on x1 cross x2. Now let us see what this x1 cross the singleton set x2 represent. This is precisely if we are taking This one is representing set x1, this is representing set x2, and this is an element x2 of this set x2. Then this particular slice, this is representing x1 cross the singleton set x2. It is to be noted here that we can define a function f from x1 to x1 cross the singleton set x2 such that f of x1 is equal to ordered pair x1 x2. It is clear that this set, which is nothing but x1 cross the singleton set x2, and if this is x1 and if this is the map, then this map or this function is a bijective function. Also, simply it can be seen that this is continuous plus open. Just think on it. And if this is bijective, continuous and open, what we can conclude that this space, that is a subspace of x1 cross x2, this is homeomorphic to the topological space x1 tau 1, or let us write only x1. Similarly, we can construct another subspace and that can be visualized like this one. Let us take again, this is the set x1 and this is the set x2. Now, if we are taking an element of this set x1, question is, if x1 is an element of x1, what about this singleton set x1 cross x2? Obviously, this is a subset of x1 cross x2, and this is nothing but a vertical slice like this one. Again, we can define a function g from x2 to this set, that is singleton set x1 cross x2. This function is given as g of x2 as this ordered pair x1 x2. So we are defining a function like this one. Note that again this function is bijective plus continuous plus open. So we can conclude that the topological space or the subspace x1 cross x2 is homeomorphic to topological space x2. This is the key step for proving the product space is connected, because these are going to play the key role. How these will play the roles? We already know that x1 tau 1 and x2 tau 2, these are connected topological spaces. As connectedness is a topological property, this is homeomorphic to topological space x1 tau 1, and we have seen that this subspace is homeomorphic to topological space x2 tau 2. Therefore, we can conclude that this x1 cross this singleton set x2 and singleton set x1 cross this set x2, both are connected. Here we have taken x2 as an element of the set x2, and also we have taken x1 as an element of x1. Now, if these are connected, one question comes whether their intersection is empty set or non-empty, that is, whether they are disjoint, that is x1 cross the singleton set x2 intersection. Let us take the singleton set x1 cross x2. Note that this will always be non-empty. Even the element x1 x2, this ordered pair will always belong to this intersection. We can also visualize it, and this can be visualized in this way. if this is the set x1 and this is the set x2, we have taken an element x1 here, and if we are taking an element x2 here, let us see what the singleton set x1 cross x2 means, that is this vertical slice, and what this x1 cross the singleton set x2 means, that is this horizontal slice, and both are intersecting at this point, and this point is nothing but ordered pair x1 x2. Now, if their intersection is non-empty, what we can conclude from here? We can say that this x1 cross this singleton set x2 union the singleton set x1 cross this x2. This union is connected. We have already seen that union of connected sets is connected provided their intersection is non-empty. Now, by using the connectedness of this union, we can construct some other sets, and for that let us fix an element. Let us take that element is, for example, a in x2, and let us take any x belongs to x1. That is, we are taking an arbitrary x from x1, and now take this x1 cross singleton set A. This is a subset of x1 cross x2 union. We are taking this singleton set x cross x2. Let us denote this set as a new set or by Cx. We are using this notation as we have already seen that this is connected. Now, if we want to visualize what is it, note that this is representing these sets. We have fixed A here if this is our x2, and if this is our x1, corresponding to every x, we can construct a tx. So what will happen? This is this horizontal slice, and now this is corresponding to every x belongs to x1. We can construct these vertical slice, and if we are constructing these vertical slice, what we can say that for all x belongs to x, if we are taking a set of this four, their intersection will always be non-empty. Now, if we are taking union of these Cx, x belongs to x1. Let us take, or if we are taking this one, this will always be connected, as this is union of connected sets with their intersection is non-empty. But one of the interesting thing is also here that this union is precisely, this is Cartesian product of x1 and x2. That is also clear from this diagram. Therefore, we conclude that the space x1 cross x2 with product topology, this is connected. Further, if we are having some finite number of topological spaces, let us take x1 tau 1, x2 tau 2, continue up to xn tau n. These are connected topological spaces. We can generalize our result, and we can conclude that the product space, that is the product topology on Cartesian product of these sets, this is also connected. We will use this result to discuss about the product topology on Rn, but before that we require the concept of connectedness of set of real numbers, which we will discuss in the next lecture. These are the references. That's all from this lecture. Thank you.